For magnetic flux, you need to refer to the equation. So the first port of call will be to look at the equation list and write down what the equation is. So magnetic flux equals magnetic flux density multiplied by cross-sectional area. As a reminder, magnetic flux is symbol phi, and that's magnetic flux density multiplied by cross-sectional area. You will notice, however, that this is out of 2 marks, and for the second mark, what they're looking for is the idea that the magnetic field is normal to the plane of the area. So if our plane is there, then the field lines are all at right angles. So you just had to make a statement that the field is along the normal to the plane of the area. For part B, you've got an experiment and you need to talk about the idea of this thing called electromagnetic induction. So the solenoid, posh name for a coil of wire, is connected to a variable voltage, and that's direct current. A coil X is placed close to one end of the solenoid. The current in the solenoid is reduced. Figure 3.2 shows the consequent variation of the magnetic flux density when it's at right angles to the plane of the coil X with time t. So coil X has a radius of 3.2 centimetres and there's 180 turns. The first thing to consider is why they've written centimetres. So that needs to be converted into metres. So get into the habit of circling the key things and converting it. So in this case, you can either do 3.2 times 10 to the minus 2 metres, or I just tend to prefer just turning it more obviously into metres, so 0.032. And then the significance of 180 turns, well, that means N equals 180. So for part I, we need to explain why the induced EMF across the ends of the coil has a constant value from time equals 0 to time equals 2.5 seconds. So you need to notice that on the y-axis is the magnetic field strength and not the EMF, and that's what you need to be talking about. So because it's a constant rate of change, in other words, it's a straight line, then what you get is a constant value of a voltage. So the answer for this would be a constant rate of change of magnetic flux. So because it's continually to get less at a steady rate, at a constant rate, then therefore you'll get a constant value of EMF. For part 2, we need to calculate the magnitude of the induced EMF across the ends of the coil from time 0 to time 2.5 seconds. So for the first mark, we need to remember the right equation, and that is that the EMF is the same as the rate of change of flux linkage. In other words, EMF is equal to delta n phi, change of flux linkage, and then the rate being delta t. So now it's a case of plugging in the numbers to find out what the EMF is. So we know from previously this information, we know that N is 180, number of turns. We know that phi equals something else, B times A. So let's just have a reminder of what B and A are. Well, for B, we're looking for the difference, the rate of change, or so the amount of change. So we've got 1.4 just here, take away 0, so our value for B will be 1.4, and again, don't forget to look at the units, times 10 to the minus 2. Now earlier we saw about the radius, and we mentioned we need to convert it into 0.32. So pi r squared gives us the area, so 3.14 roughly times 0.032 squared will give us the area. So bringing that forward, so 1.4 times 10 to the minus 2 for B, multiplied by pi r squared don't forget to square it, and then the time taken, well again, flick back to the graph, I think it tells you elsewhere too, but we're looking over a period of 2.5 seconds. And that then comes out to be 3.2 times 10 to the minus 3 volts. Figure 3.3 shows a transformer circuit, so we need to note all the information that it gives us, so 1,000 turns turning into 25 turns. So assuming that, and it does say here actually, that the left-hand side is the primary coil, that makes the right-hand side the secondary coil. So because the number of turns goes down, we know it's a step-down transformer, so that means the potential difference will go down. So in addition to that, we know that the lamp is connected to an output of the secondary coil. The potential difference across the lamp is 6 volts. So that's just here. So I would add that in there. So we know that V out is 6 volts. And the lamp dissipates 15 watts. So as soon as you see the word watts and power, and then this topic, you need to think, okay, how are we going to get some current? How are we going to get some potential difference? So the link there, look on the physics equation sheet, power equals current times volts. You might need it, you might not. And in this case, we're assuming that there's 100%. So if it is 100% efficiency, no energy gets lost. So we need to calculate the current in the primary coil. So first thing to do is a bit of logic. What do we know? Well, we know this information over here. So we know the power in the secondary coil is 15. And we know the voltage, or potential difference 6. And then we can find the current in the secondary coil. So in the secondary coil, 15 divided by 6. So I think that's about 2.5 amps in the secondary. But of course we want to find it in the primary still. So now with some logic, we know on the right hand side, the secondary coil, there are 25 turns and there are 2.5 amps. So if you multiply those two together, that gives you 62.5 as a ratio. And then because it's 100% efficient, we then know that on the left hand side, that's equal to 1,000 multiplied by the current. And then it's a case of rearranging for the current, 62.5 over 1,000. So just in case you didn't follow. So with transformers, it really is down to the ratios. The left-hand side equals the right-hand side. So the number of turns multiplied by the current on the left-hand side, the primary side, equals the number of turns on the secondary side multiplied by the current. That could equally be voltage as well. But in this case, we know the number of turns on the right-hand side, 25. We calculated the current, 2.5. We know the number of turns this side, so we just needed to find the unknown. And then finally, the alternating voltage supply is replaced by a battery. explain why the PD across the lamp is 0 sometime after the battery is connected. So the key thing to know about a battery is that it is direct current, so current only flows in one direction, so you don't get a change in the direction of the current that is flowing. And as a consequence of that, it means that there's no change in the flux density, or there's no magnetic flux linkage. Key word to use there is flux. You need something to be continually moving, to be continually changing. So if the current isn't doing that, then you don't get the change, and therefore you don't get a PD.